Interference is a phenomenon exhibited by all types of waves. When identical waves from two sources overlap at a point in space, the resultant wave intensity at that point can be greater or less than the intensity of either of the two waves. This phenomenon is called interference. Here, identical waves mean that the interfering waves have the same frequency and amplitude, and the phase difference between them is constant with time. When the resultant intensity is greater than the individual intensities, the interference is said to be constructive. If the resultant intensity is less than the individual intensity, then the interference is destructive. The phenomenon of interference can be explained on the basis of the superposition principle of waves. According to the superposition principle of waves, at a particular point in the medium, the resultant displacement produced by a number of waves is the vector sum of the displacements produced by each of the waves. Let us understand the superposition principle and the interference of waves by considering the waves on the surface of still water. Two needles are placed above the water surface and made to oscillate up and down periodically. The 2 points S1 and S2, where the needles dip in the water, act as the two sources of waves. Let P be a point on the surface of the water. When waves generated at S1 reach the point P, the point executes simple harmonic motion. Let y1t be the displacement of the particle P due to waves from S1. Similarly, when waves generated at S2 reach the point P, the displacement caused is given by y2t. If waves from both S1 and S2 reach the point P simultaneously, the resultant displacement yt is given by the superposition principle as yt is equal to y1t plus y2t. If waves produced by two sources have the same frequency and the phase difference between them does not change with time, then such waves are said to be coherent, and the two sources are called coherent sources. Let us assume that the two sources S1 and S2 are coherent and generate waves of amplitude A and angular frequency omega. Consider a point P on the perpendicular bisector of the line joining the two sources S1 and S2. For such points, S1P is equal to S2P. Since both the sources are at the same distance from P, the waves reaching the point P are also in phase. If the displacement produced at P due to the waves generated at the source S1 is given by the equation y1 is equal to a cos omega t, then the displacement at P due to the waves from S2 can also be represented by y2 is equal to a cos omega t. We know that the intensity of a wave is proportional to the square of its amplitude. Therefore, if I0 is the intensity produced by each of the sources, then I0 is proportional to a square. The resultant displacement at P, y is equal to y1 plus y2. On substituting the values of y1 and y2, we get y is equal to 2a cos omega t. If I is the resultant intensity at P, then I is proportional to 4a square. In terms of intensity of individual waves, I is equal to 4I0. The resultant intensity is 4 times the individual intensities. Hence, we say that the two waves interfere constructively. Now consider a point Q such that S2Q minus S1Q is equal to 2 lambda, where lambda is the wavelength of the waves. Here, 2 lambda is the difference in the distance travelled by the waves to reach the point Q and is known as the path difference. The waves from S2 will reach the point Q 2 cycles after the arrival of the waves from S1. Hence, the path difference of 2 lambda is equal to a phase difference of 4 pi, and the phase difference between the waves arriving at the point Q is equal to 4 pi. If the displacement produced at the point Q due to the waves from S1 is given by y1 is equal to a cos omega t, then the displacement produced by waves from S2 is represented by y2 is equal to a cos omega t minus 4 pi. But this is again equal to a cos omega t. The resultant displacement of Q, y is equal to y1 plus y2. On substituting the values of y1 and y2, we get y is equal to 2a cos omega t. And the intensity will be again equal to 4I naught. Now, let us consider another point R such that S2R minus S1R is equal to minus 2.5 lambda. Since the path difference between the two waves reaching the point R is 2.5 lambda, the corresponding phase difference would be 5 pi. This means that the waves from S1 will arrive exactly 2.5 cycles later than the waves from S2. Thus, if the displacement produced at the point R due to the waves from the source S1 is given by y1 is equal to a cos omega t, then the displacement due to the waves from S2 will be y2 is equal to a cos omega t plus 5 pi, which is equal to minus a cos omega t. The two displacements y1 and y2 are out of phase. If the net displacement at R is y, then y is equal to y1 plus y2, which is equal to 0. Hence, the intensity at R is 0. The two waves are said to interfere destructively, and this is known as destructive interference. Hence, if waves are emitted by two coherent sources like S1 and S2, the general condition for constructive interference of these waves at a point P is the path difference between S1P and S2P must be equal to n lambda, where n is a positive integer. Let this be equation 1. At the point of constructive interference, the resultant intensity is 4 times the individual intensities. If the point P is such that the path difference between S1P and S2P is equal to n plus half into lambda, where n is a positive integer, then we will have destructive interference. Let this be equation 2. For destructive interference, the resultant intensity is equal to 0. Since the two sources are coherent, the resultant intensity at any point does not change with time. If the two sources emit waves continuously, constructive interference takes place at some points and destructive interference at other points. That means, points for which equation 1 is satisfied, constructive interference takes place, and the intensity at those points is 4 times the individual intensities. For other points, where equation 2 is satisfied, we have destructive interference and the intensity is 0. The curves shown in the image form the locus of all points for which the path difference is an integral times the wavelength. They denote all points on which constructive interference occurs. In between these curves, we have curves indicating the locus of all those points for which the path difference satisfies equation 2. Note that, in case of interference, the energy is redistributed. Consider an arbitrary point E such that the path difference between S1E and S2E does not satisfy the condition for either constructive interference or destructive interference. Let the phase difference between the displacements caused by the two waves at the point E be phi. At the point E, if the displacement caused by the waves produced at the source S1 is represented by y1 is equal to a cos omega t, then the displacement caused by the waves from S2 will be y2 is equal to a cos omega t plus phi. The resultant displacement at E will be y is equal to y1 plus y2. Substitute the values of y1 and y2 in the above equation. And on further simplification, we get y is equal to 2a cos phi by 2 into cos omega t plus phi by 2. The amplitude of the resultant displacement is equal to 2a cos phi by 2. Therefore, the intensity at E is I equal to 4a square cos square phi by 2. This can also be written as 4I naught cos square phi by 2. Let this be equation 3. Equation 3 is a general expression which enables us to find the intensity at any point on the surface. If the phase difference phi is equal to 0, or plus or minus 2 pi, or plus or minus 4 pi, and so on, then cos phi by 2 is 1, and hence I is equal to 4I naught. These points represent the interference maxima. This is the general condition for constructive interference in terms of phase difference. If the phase difference phi is equal to plus or minus pi, or plus or minus 3 pi, and so on, we will have destructive interference leading to zero intensity. These points are the interference minima. This represents the general condition for destructive interference in terms of phase difference. If the two sources are coherent, then the phase difference at any point does not change with time. Hence, the interference pattern formed is stable. If the phase difference phi is not constant and changes with time, then the interference pattern formed will also change with time. The positions of maxima and minima will also change with time. If these changes happen very rapidly, we observe a time-averaged intensity distribution. Mathematically, the average intensity is equal to 4I naught into the average of cos square phi by 2. But we know that if phi of t varies randomly with time, the time-averaged value of cos square phi by 2 is equal to 1 by 2. In such cases, the resultant intensity is given by I is equal to 2I naught. That means the two intensities are just added up. So we need coherent sources to produce a stable interference pattern.